Hello and welcome to the presentation. Today we're going to be talking about our project, which was predicting and explaining injury severity in car crashes, and is presented by Team 3. All right, so we are Team 3.
I'm Tarun from doing my master's in management information systems at OSU. So I worked on data preparation portion of this project.
I'm Egan Galvin. I'm going through the graduate certificate program in data science, and I also worked on the data prep for this project.
Hello, my name is Darren Cartwright. I'm working on a master's degree in MIS with focus in cybersecurity. I worked on the data modeling and business understanding portion of this project.
Hello, my name is Amir Razai. I'm a grad student in MIS program, and I mostly worked with the models, machine learning models in this project.
Using the available accident, distract, person, and vehicle data, we use the CRISP-DM methodology and various modeling methods to predict and explain injury severity in car crashes. After we prepped the data, we used number-based and set-based machine learning techniques to find the correlation between various variables to see if we can answer the above question of predicting and explaining injury severity in car crashes. We chose the random forest analysis and the naive Bayes classification for high accuracy and area under ROC curves. All right, so a quick recap of the CRISP DM methodology steps. 1, we have business understanding. 2 and 3 are the data understanding and data preparation steps. 4 is the model building. And then 5, we have testing and evaluation. And then we will touch briefly on 6, deployment.
As Egan described before, we hope with this project to identify and predict the severity of automobile crashes based on relevant data surrounding the crash. We'll be using 5 main models and find correlation between the independent variables in the data set. We found that the biggest use of this data information would actually come from first responders, such as police and ambulances, because if you were primed to understand that the car crash might be incredibly severe, then there's a good chance you'll have more of a hustle, reach there further, and save innocent civilians, which would be good for both a business perspective and a civilian perspective for driving on the road.
So the second step in the CRISP-DM methodology is data understanding. We had a number of variables across multiple data sets that were imputed. We decided that we weren't going to use those variables for this project. We were going to impute our own variables. Second, we wanted to use a variety of variables that would help us with our prediction. So we used anything that related to the person, which age, region, alcohol or drugs. And then we also wanted to use any variables that would pertain to the crash itself. So light conditions and weather, or even model year and travel speed.
So coming to the data preparation, we first started using joiner node to join all separate data files. And then we filtered out injuries severity variables. Afterwards, we filtered body type to only include consumer used vehicles. This excluded vehicles such as motorcycles, buses, and heavy trucks. So once we filtered out the body type, we then filtered out the other seat positions that weren't the driver, so that we can focus our prediction around the driver of the vehicle. Last variable to be filtered was the deformed variable. We filtered out all variables that would indicate no deformation to the vehicle at the time of crash. Here are the variables that we picked to do our project. We mainly focused on the driver, like his gender, whether he consumed alcohol or he's on drugs, and also the environment conditions around, like weather conditions, road conditions at the time of crash, like surface conditions, and also whether the vehicle is carrying drug or some harmful chemicals or not, and the speed of the vehicle, and also the injury severity and the lightning conditions at the time of crash. After picking our desired variables, we used a numeric binner to filter out some specific variables, like day, week. We binned this variable into either a weekday or a weekend. And And for airbag, we binned this variable into either one airbag having multiple airbags or no airbags deployed. And also the weather condition, whether it is non-severe weather, rain type weather, or wind type weather, or other. And also towing vehicle, we binned this variable into no trading units, fixed linkage, or non-fixed linkage. After binning, we use rule engine node to get rid of any unknown values or missing values. And also for the data containing numeric values, we use something like median to replace the missing values for vehicle age, travel speed, speed limit, to simplify some of our values into variables that are more easily understood.
For the model building, we deployed 5 machine learning models for this problem: decision tree, random forest, naive Bayes, and multi-layer perceptron artificial neural network, and probabilistic artificial neural network as well. Decision tree, as always, is our first to-do model because it gives us a good sense about our variables and it's easy to interpret. But in this case, we didn't get a good accuracy from decision tree, probably due to overfitting. But we got 67.2% area under cover, area under curve. I'm sorry. And on the right-hand side, we have three levels of splitted variables in decision tree. Well, the second model is random forest, which is a collection of decision trees and gives us a better accuracy with the accuracy of 77.1% and area under curve of 75.3%. And on the right-hand side, we have the variable importance. As we can see, the deformed bin and the rest missing, and also the first harmful missing, were the most important variables in the random forest model. Our third model was multi-layer perceptron artificial neural network. It gives us the accuracy of 71.2% and area under curve of 76.6%. With this accuracy and area under curve, this model can handle reasonably good for predicting the severity of the injury.
Thank you, Amir. The next model that we used was a naive Bayes classifier. This model utilizes Bayes' rule to make predictions, which is taking the probability and having that be equal to the likelihood times prior probability of events with model evidence, and it's all recursive with backpropagation. Each variable is assumed to be an independent part of the dependent variable, making it making prediction based on the very important variables and helps with sticking out. However, it isn't as nice and clean to look at as the decision tree or random forest. This model did give us a very good mix of accuracy and area under curve, however, with an accuracy of 75.8% and an area under curve of 74.8%. The ROC curve is shown on the right. Our next model that we used, and the final one for our project, was the probabilistic artificial neural network. This had the lowest accuracy by far at 50.1%, being no better than a coin flip, but it did have a surprisingly decent area under curve of 71.4%. This suggests a moderate ability to distinguish between high and low injury. It was much better at distinguishing low injury than high, but so bad high that it couldn't do well. And this model is based mostly on distribution models, or distribution and with normal curves.
Our last model was k-fold cross-validation with LR, logistic regression. It was a very reliable method for binary classification, and it gives us the accuracy of 69.8% and area under curve of 77.2%. And you can see the ROC curve on the right-hand side.
Thank you, Amir. For the k-fold validation, we did do that 10 times and use that as the benchmark for comparing. And here we can see our overall ROC curves combined. They're all very similar, with the decision tree analysis lagging behind noticeably. But once you get into the MLP, artificial neural network, and the random forest, and the MLP neural network, it's all very lined up close to one another. So what did we decide to go with? Well, comparing all of them together, we can see with the accuracy rankings, it went in the order of random forest analysis, naive Bayes classifier, MLP artificial neural network, decision tree analysis, and a probabilistic artificial neural network. The area under the curve was similar, but slightly swapped around. In this case, the MLP artificial neural network got first place. And then going down the line, it's random forest, naive Bayes classifier, probabilistic artificial neural network, and the decision tree analysis. Overall, we recommend using the random forest and or naive Bayes classifier and giving this to police dispatch units. Both of those models had a good mixture of accuracy and area under the curve where it felt very reliable to give. The MLP was a close choice, however, with the accuracy of 71% thereabouts, we didn't feel quite as comfortable as above 75%. This would be excellent for first responders because it would be pretty simple to introduce. There's not a lot of heavy lifting that needs to go into making the model function. And they could ask specific questions for receiving information on a car crash to prime their response. So, for example, if a car crash happens and the model predicts it's bad, even if though there's a slight wiggle room that it might not be bad, that still gives more of a response to tell the police officers in question or the ambulances, hey, you need to go and do that right now. This person might die. And if that's the case, then the minutes that could be saved in this process could save lives. And that is what we're trying to do, first and foremost, saving the intangible and tangible cost of crashes as they evolve over time. More research will need to be done, and as more data is collected, the model may become stronger over time. However, we do still feel as a team that this is a worthwhile research project to look into. Thank you.